This is another problem on the operational amplifier. These are two operational amplifiers. Both of them are treated as ideal, and our objective is to find out the value for the output voltage V0. So looking at this particular circuit, if we concentrate only on this part of the circuit, then we find that this turns out to be a voltage divider. So as I mentioned before, with a voltage divider, you have some source, let's call it as Vs, and then there are two resistances in series, R1 and R2, and R2 goes to ground, and we are interested in this midpoint voltage, which is referred to as Vx, and then Vx is equal to this resistance R2 divided by sum of both the resistances, so R1 plus R2 multiplied by Vs. So if we look at this part of the network, here is one resistance R1, this is the second resistance R2, goes to ground. Here Vs and V0 are equivalent, and therefore the voltage at this node can be given by 1 kilo ohm divided by 1 kilo ohm plus 3 kilo ohms multiplied by V0. And so if we call this voltage as Vx, then Vx will be equal to 0.25 times V0. So this comes from the concept of the voltage divider, and then using the concept of virtual short, we know that if this node is at 0.25 V0, then this node will also be at 0.25 V0. So once we have done that, we can replace that entire voltage divider network with this 0.25 V0 and then go ahead with solving the rest of the circuit. So note that if this is 0.25 V0, voltage at this node is 0.25 V0, and then we can mention this voltage as maybe Vp, and so we can frame one nodal equation as, if this is the current I1 that flows from this 1 volt source, then that is the same current that should flow up until this node, because the op-amp's input terminal does not draw any current. So if I1 is equal to I2, I1 is represented by 1 volt minus of 0.25 times V0 divided by 1 kilo ohm, and I2 will be represented as 0.25 V0 minus of Vp divided by 2 kilo ohm. So we go ahead with doing this little algebra, and we can find out the value for this Vp in terms of the output voltage V0, and this is given by Vp is equal to 0.75 V0 minus of 2. Next, if we concentrate on this op-amp, then we note that the voltage at the non-inverting input terminal is negative 1 volt, and again using the concept of virtual short, we can note that the voltage over here at this node should also be negative 1 volt, and therefore if we call this current as I3, so I3 and I4 should be the same, because once again, if this is the current I3, no part of it can enter the input terminal of the ideal op-amp, and therefore the entire current has to flow into the op-amp from its output terminal. Also note that generally there is a small misconception among students where they claim that I2 and I3 are same, but note that I2 and I3, these are not same at all, because it could be that if this is the current I2 flowing up to this node, some part of it may enter the op-amp through its output terminal, or the op-amp might source some current, and so I2 plus the current that is sourced by the op-amp will be equal to I3. So the point to note here is that we cannot frame a nodal equation over here because this current currently is unknown to us. Okay, so looking at this node, we know that I3 is equal to I4, and therefore we can frame the expression for I3 as Vp minus of minus 1 volt divided by 4 kilo ohm, which should be equal to minus of 1 volt minus of V naught divided by 8 kilo ohms. And so this is that expression. If we go ahead with this little algebra, it results in V naught, where Vp substitution from equation 1 can be done. And so if we write this as 2 times Vp, so this becomes 2 times 0.75 V naught minus of 2. And then going ahead with the little bit of math, we find that V naught is equal to 0.4 volts. So basically this question considered the concept of a voltage divider at first. Secondly, for both the op amps, we used the concept of virtual short, and we noted the voltages at this node and this node, and then applied nodal equations twice. So this is one node that we considered, and this is the second node that we considered.